We're going to transition into our last session, which is about health of people. If you're exiting the room, that's fine, but just please do so quietly. It's my pleasure to introduce our first speaker for the last session, who is Dina Katabi. Dina is the Tuan and Nicole Pham Professor in MIT CSAIL, as well as leader of the NET MIT Research Group and co-director of the MIT Center for Wireless Networks and Mobile Computing. Those of you who were able to join us yesterday morning might have heard Dina talk briefly about superpowers, and we've brought her back today to talk about her superpower of seeing through walls to help assess human health or other topics that she might care to tell us about. Welcome, Dina.
So, hi everyone. Today I want to talk about neurological diseases and therapies. So basically when we talk about diseases, neurodegenerative diseases like Alzheimer's, Parkinson's, ALS, or we talk about mental health, depression, bipolar, schizophrenia, stuff like that. And where AI can help us and how it can help us both in understanding the disease, but also in understanding the therapy and their effectiveness. And again, I'm going to introduce you to some of the older research that we did, and as we progress, show you some of the results that's not published yet that we have in depression. Okay, so how can we use AI to understand neurological diseases and their therapy? So one of the problems why it's very hard today to deal with mood disorders, depression, bipolar, anxiety, and neurodegeneration as well, we don't know how to measure them. We can't measure the brain, and we can't measure the behavior. And we measure them in animals. So you put electrodes in the brain of a mouse, and that Alzheimer in the mouse is not the same as the Alzheimer in the person. Or depression in a mouse is definitely not depression in a person. So how can we measure brain and behavior in people? Unfortunately, what we do today is we ask them to self-report. Somebody comes, like the doctor will come and ask me, oh, Dina, how do you feel? Is this drug making you feel better? But this is very subjective when it comes to mood or cognition or these kind of things. And if we can't measure, we can't understand neither the disease nor the therapy. So my claim is that ideally, we want AI and all of this advancement in neural networks to help us in measuring the brain and the behavior. Now, I want to make another claim, is that when we want to measure in neurodegeneration or in mental health, you really want to measure in a completely passive way. One of the unfortunate things about MIT is that actually we do have depressed students, and I dealt with multiple depressed students throughout my career here at MIT. And I can tell you one thing, when people are depressed, they just don't want to interact. So asking them to measure themselves during that time is not going to happen. They withdraw, and when they are in pain or in depressed, typically, people don't want to measure or do anything. So if we want to measure them, we want to be completely passive and not asking them to put any effort. And that's very important, both for mood disorder and for neurodegeneration, because in neurodegeneration, you are dealing with Alzheimer, Parkinson, these people who are older, less savvy in terms of measurement and computation. So how can we measure someone completely, measure their health completely passively, as they live their life? So here's what I'm proposing. We can use something that looks like your Wi-Fi box at home, a device that sits in the background of the home, analyze these radio signals that bounce around of our bodies, and from that, analyzing them using neural network, and from it, it can get motor symptoms in Parkinson and similar disease, sleep and sleep behavior, breathing and vital signs. It can get even behavioral symptoms and interaction with a caregiver completely passively. In fact, this is not science fiction. We have this device. We have developed it and did the initial results, initial research at MIT. We call it the Emerald device. And it is enabled by AI, by neural network that analyzes radio signals that bounce around. Let me show you some examples from the lab, and then I move and show you example with patients with depression. So this is one of my students, and this is the office here in CSAIL, and the device is not even in the same room. We're going to monitor him through the wall using our wireless device from the adjacent office. This dot here is where the device thinks that he's standing right now. Let me play it for you. Look how the red dot is tracking his motion. Now, we don't ask him to wear any devices. He's not wearing like accelerometers or having cell phones or anything, but we can still track him very accurately through a wall. Right? So that, of course, is important for diseases that are related to motion disorder, neurodegenerative diseases like Parkinson's, for example. And our tracking is actually very highly accurate, and we have peer-reviewed results that show them. But once you have the location of the person over a floor map, now you can ask about behavior, and you can quantify behavior. Because you can start, for example, asking, is this person showing withdrawal impact? So he's like waking up, he's staying in his bed, tossing around for a long time, hardly ever sees anyone, hardly goes to grab food, goes back to the room. And in particular, if this is not his general behavior, that this withdrawal symptoms that are appearing on him, that would be alarming, and you can start to quantify that. What else can we measure? When you go to sleep, your brain waves change and enter different stages: awake, light sleep, deep sleep, rapid eye movements, or REM. And these sleep stages are very much a platform for all neurological disorders, from neurodegeneration like Alzheimer's and Parkinson's, of course, to mood disorders like depression, anxiety, bipolar. Just to give you an example, people who have depression typically have REM happening early during the sleep. And in fact, one of the impacts of antidepressant is to delay REM. So today, if you want to get this accurately, you send someone to a sleep lab, they put these electrodes on their dumb body. Yeah, you can tell he's not happy. So now let me show you the better alternative. Okay, so here's our wireless device. Transmit very low power wireless signal, 1,000 times lower power than Wi-Fi, and analyzes the reflections, and from that gets the sleep stages. What you see up there is something called a hypnogram. So when you send someone to a sleep lab and they put all of these electrodes on their head and body, you get a hypnogram. You get something like this. But look at this guy sleeping in his own bed without anything. You can get this every night without disturbing the person, without causing them depression just to deal with all of these things on their head and body. Okay, and of course, everything that we do is highly accurate as compared to the gold standard. Now, this person is sitting like you, and what you see here is his breathing, inhales, exhales. We ask him to hold his breath, and you see the signal stays at a steady level because he inhaled, he did not exhale. And again, everything is compared to the gold standard and FDA-approved clinical devices. So over the last 4 years, we have been working with medical doctors, pharma companies, hospitals, and a variety of diseases, particularly in diseases that are related to neuroscience, like Alzheimer's, Parkinson's, depression, and Rett syndrome. And I'm going to show you some results. One result for neurodegeneration, Parkinson, and one result in Alzheimer. In depression for mood disorder. So let's talk about neurodegeneration. So we all know that diseases like Parkinson's and Alzheimer's affect the elderly. They are quite common. In fact, Parkinson's is the second most common neurological disease, and it is the fastest growing neurological disease in the world. So it is the second after Alzheimer in the number of people, but it is the fastest growing today. So one of the problems with Parkinson's, similar to Alzheimer, is that we diagnose the disease late. We know that the disease started in the brain potentially 5 to 10 years earlier, But to diagnose the disease, we wait until we have the motor symptoms, because this is our sign, like people start having tremor and stiffness in motion. But the problem is that by the time they have these tremor and stiffness in motion, the neurons, the dopaminergic neurons in the brain that are the essence of that disease, 40 to 80% of them are already dead, gone. Okay, so if you diagnose a disease at the time when actually 80% of the damage is already occurring and happened, then what are your chances in treating the disease? And indeed, there are very, very little chances in being able to deal with Parkinson's today. So we need to diagnose Parkinson early, and we need to diagnose it from something other than motor symptoms, because motor symptoms happen late. What can we do? How AI can help us here? So AI would allow us other signals. So we went and looked at the literature, the medical literature related to Parkinson's disease, and we noticed that even as early as the first set of studies from Dr. James Parkinson himself, he says that the breathing of the patient changed. So we asked a very simple question: can machine learning take the breathing of somebody and tell whether they have Parkinson's or not? Doctors cannot do this. I can tell you, because my collaborator is like, okay, good luck. Okay, but let's see whether AI can do it. So we trained a neural network to take one night of a breathing signal and go through a neural network. And the neural network is going to answer two questions. Does this person have Parkinson's? And if they do have Parkinson's disease, what is the severity of their disease according to the gold standard? And this is a very large study that ended up in Nature Medicine last year, and with like over 7,000 patients, 700 of them have Parkinson's and the rest don't. And it involved MGH, Mayo Clinic, and University of Rochester. So what do you think? What do you expect the accuracy of being able to tell whether someone has Parkinson's just from their breathing? Just make a guess. What? 20%? Okay, let me show you this. Not only from their breathing that we collected through wireless signal, you get an accuracy that's about 90%. Okay? This is actually not for wide variety of severities, from very early in Parkinson's to very late in Parkinson's. And so if you haven't seen those graphs, I mean, this is called the ROC curve. On one axis, there is specificity. On the other axis is sensitivity. The important number is this AUC, which you can interpret it as accuracy. And in fact, not only you can get it from wireless signal, like you can also put breathing belt on the individual, get that breathing signal, and go through and you get more or less the same accuracy. So the machine can see something we as humans can never see in a breathing signal. Not even the best neurologist who's expert on Parkinson can do that. Just because machines see the world in a different way. So in many cases, people want to make AI, make machine as good as humans. I think actually the area where things can be really, can change, can be revolutionary, is when we use machine learning, when we use AI to augment our capabilities and our ability as humans to see signal, to see things in what is around us, to get us to the next level, to solve problems that we can't solve today as humans. Okay, so the next question you can ask, okay, but Dina, you told us that we can ask the question, can we detect Parkinson early, before it's diagnosed? And this is a very interesting question. And the problem with that, of course, we need to do the measurements with people before they are diagnosed, so we don't know who's going to develop Parkinson later. But it happens that there is a small study where people collected the nocturnal breathing signal during 2 visits that are separated by 6 years. So there are some people who came in the first visit and said, I don't have Parkinson's. And then 6 years later, when they came for the second visit in that study, some of them, a small percentage, said, I have Parkinson's. So sometime between, like, over these 6 years, some of those people have Parkinson's. So let's see whether we can already tell from the first visits whether those people have Parkinson's disease. Okay, so the people who eventually developed Parkinson's are in blue. The people who did not have Parkinson's, did not develop Parkinson's disease are in red. And you can tell that the machine, for 75% of them, already is saying, I think those people have Parkinson's. I mean, they look different to me. So this is very interesting. Of course, this is like an initial study. To be able to get the full power of this, we need to expand this to much larger studies and look at different types of Parkinson, because Parkinson is not just one disease. Actually, it's an umbrella. So we need to do studies, but it shows us the power of machine learning when actually it is used for generating new data in medicine. Now, one other thing that I'm interested in is mental health. I really believe that it shouldn't be that in mental health we completely just ask questions. Like, we should be able to have quantifiable markers that say this person is more depressed than this person, this drug has this efficacy level within even the individual person. So how do we do this? We need to measure the brain and measure these things without putting electrodes in the brain, of course. So one of the things is that we looked at is, can we detect the impact of antidepressant on patient? And who's taking antidepressant and who's not, and whether the antidepressant is engaging the target or not. So I can tell you today, I can look at someone's sleep and I know whether they are taking antidepressant or not, with very high accuracy, not just me, my students. You guys can look at that data, can look at your sleep. You can't hide from them if you are taking antidepressant. Okay, so what does that mean? So first, I have to explain to you, this is sleep, this is a hypnogram. When you go to a sleep lab, they give you something like this. So this person went to sleep slightly before midnight, and then this is sleep onset, and then after that, he entered light sleep, deep sleep, and then REM is the stage in which we dream, and it is the mood regulator. So these are all REM, and sleep happens in cycles. I'm sure all of you have heard. So this is the first sleep cycle, the second one, the third one. The last one here ends with awakening. Like you don't typically sleep cycle end with REM, but it can also end with awakening. Okay. So if you have all of that data from the home, night after night after night, and you want to analyze REM, which is the mood regulator, then we want to have some visualization that allow us to do this. So what we are going to do, we're going to just take these episodes of REM and put them in color. And episodes that don't have REM, whether it's light or awake or whatever, we're just going to ignore them. We're going to set them to 0. Okay, and this is what we are going to get. Let's talk first about somebody who's not taking antidepressant. So 0 is sleep onset. Every time you see color, it means the person enters REMs. Every time you see black, the person is not in REM. And these like night after night after night. And you can very clearly see that people have very regular sleep. Like almost every night you enter REM around the same time. This is a person who's not taking antidepressant. This is a person who's taking antidepressant. What's happening to them? Their first REM sleep got knocked off. So when people, like in the literature, tells you about antidepressant, we know, like the literature tells you that antidepressant delay REM. But actually, it's not delaying REM. What's happening is that it's knocking off the first REM, and if you don't know that there is a first REM that was here because you don't have much data, you are looking only at one night, you think that it is just delayed. So that's very interesting, why it knocks off the first REM cycle as opposed to the second, as opposed to the third, or all of them. That's very interesting. I mean, of course, we don't know, but my hypothesis is that there is a different balance or homeostasis of neurotransmitters in the brain in the first cycle versus the second and the third, and understanding that would be very effective. But we can tell whether somebody is taking antidepressant or not. Okay? Doesn't matter what type of antidepressant they are taking. actually, it seems to work across all antidepressants that are on the market today. So these are different types of SSRI. I'm sure you guys have heard about paroxetine, Prozac, escitalopram. So all of these are SSRI-based antidepressants. These are different types of antidepressants. So their mechanism of action is different. It's SNRI, SARI, mirtazapine is even completely different in ASSA. So it works. And when you take machine learning now and ask, from a single night, I don't want to put all of that data together. Now, you machine are going to give me some power, some additional power that I can't visually see. And maybe from one night, you can tell very accurately who is taking antidepressant or not. And then we can do something like this. So say, what is the accuracy if from one night being able to detect antidepressant? It is 86% with a new machine learning model. And now you can say, OK, so if somebody starts taking an antidepressant at a particular time, how would the machine know when exactly they started? So this is very interesting, because this patient started going on fluoxetine throughout the study. And you can see that at the beginning, the machine learning is very sure, like he doesn't take antidepressant. But when he started taking antidepressant, in fact, this effect is not immediate. So the machine started saying, I think he's taking antidepressant, but you can see that the thing is gradually getting trust. And we know that the antidepressants don't have impact immediately, actually that they take time to be completely effective. And although the machine doesn't know what is happening in the past or the future every time it looks at just one night, it is actually seeing that effect. So it is seeing indirectly how the drug is engaging the target. So this is the second person that is taking different drug, and you see similar effect. I want to end with Gen AI and say, so Gen AI, we think typically we are generating text, we are generating images. But wouldn't it be really nice if we generate medical data? If I can take very cheap data, like just a signal that bounces off you, and from that can get a full EEG picture of you. That would be generative AI. So basically, today, I can say a corgi playing a flame-throwing trumpet, and it generates this image. Tomorrow, I want to say, this is a wireless signal from Dina. Can you generate her EEG? And that might sound not feasible or a stretch. But I think it's not that far of a stretch, because actually, we started having initial results that show that this is completely feasible. So this is a patient who has Alzheimer's. This is their EEG spectrogram. And this is the generative spectrogram that we generated for them. And you can very clearly see that the EEG spectrogram that is generated for them from the radio signal bouncing around is very much similar to their actual EEG collected by putting all of the EEG electrode on them. So we can use that power to generate new medical data, high-quality medical data that will allow us to do a very initial screening of patients. So now next we can go send somebody to an MRI or something that is way more expensive, but from something very, very cheap that is available readily for everyone. Okay? So with that, let me finish by saying I think the future is really being able to get inside the brain, understand it, understand its diseases, understand its therapy with the power of AI and radio signals. Thank you very much.
Thank you, Dina. That was fantastic. I would only take one pressing, very fast question. That'll be
Thank you, Dana. That was a very, very interesting sharing. So my question is with respect to using breathing to detect early, Parkinson's disease. So the AUCs are incredibly high, I'll give you that. But the thing is, you need to control for a lot of confounders, because breathing is it has a lot of influential factors that could influence your breathing. So for instance, I think the reason why the AUC is very high is because the cohort that you're building is you eliminate other sort of like neuro disease, like
No.
other
So
sort-
we, for example, we compared with, can you like mistake somebody who has Alzheimer as Parkinson? And the answer is no. So actually it's specific to Parkinson. So I agree there are many co-founders, but actually because we trained with many different comorbidities and also we use a very sophisticated, I mean, I'm like really abstracting here so much, but there is an analysis of co-founder and we understand that. But no, actually it is separating the Parkinson. Now you can ask other questions like more detailed, like even within Parkinson, there are different like subtypes, for example, or if you have something that is very close, like palsy, for example, can you separate it or not? That would be harder. But clearly it's separating different types of neurodegeneration that is pretty close, like Alzheimer. And also another thing is actually is doing it even for people who are very early in the disease, as we saw. So it's not, so talking about breathing, I think actually breathing is very underused. It's very important signal because the breathing center in the brain actually happens to be in the pons and the medulla and very close to so many nuclei that have different factors. So it has a lot of information that are both related to what's happening to the brain, the autonomic system, in addition to the thing that we traditionally think breathing is useful for.
Yeah, thank you very much. That's interesting.